Welcome back. In this lesson, we're going to return to the field of cosmology, which, remember, is not cosmetology. It's not makeup and hair, but we're looking at the formation of the universe, and in this case, specifically, the formation of the solar system. Remember that cosmology generally completely disregards any idea of creation and is only using what we know of the physical laws to make guesses of what happened in the deep and distant past. So let's look at some of the details. The field of cosmology, if you remember, has rejected the idea of creation and is looking only at natural processes that we understand, the physics of the universe that we have been able to see and measure, and they assume that there was the existence of matter, and specifically in the form of very light elements like helium, hydrogen specifically. So given that, if that was the situation at the formation of the solar system, and that's what this lesson is looking at, formation of the solar system, then you're simply taking those ideas and using what we know of physics to make some guesses or predictions about what happened in the formation of the solar system. So the idea, if there was the presence of hydrogen gas specifically, it's very, very light, and it's nearly a vacuum. When you have very, very tiny atoms that are very far apart, there is a slight gravitational attraction. And the idea is that given enough time, those atoms will attract together and increase the density of that gas, and you'll end up with a cloud of gas. As that cloud of gas pulls more and more to itself, you are going to normally get a spin. And as that cloud then further contracts, that spin will get faster. Just like an ice skater at the Olympics, as they're going around in a turn, if they pull their arms in, the turn gets faster because of the momentum that they have, the rotational momentum that they have. So this is the first idea, that you have a collapsing cloud of gases that then starts to rotate, and then it will get faster. And as it gets faster, the matter then condenses towards the center. And so most of what you see, say, in the solar system is where most of the stars are in the center and fewer stars are on the edges. And that is just like if you were to stir the bubbles on the top of your hot chocolate, the bubbles will concentrate in the middle and be fewer towards the edges of the cup. It's happening the same way with the stars, and it's happening also with the planets. So if you were to have these gases, eventually you're going to have enough gravity that the star will ignite, and you'll end up with a star system. That very centralized star then has its own gravity around the material that's around it. And as that material contracts due to gravity, the idea is that planets could form. Now, the closer you are to the sun, the heavier that the elements that are in that area will go. So a lot of times you'll see, and especially in our solar system, the first 4 planets are rocky planets. They're terrestrial planets. As you get farther towards Jupiter and past, you're going to get gas giants, which are mostly light material. So where you are, where the elements are, will kind of coalesce at different places. And so you end up with tiny atoms of heavier materials coming together and forming little dust, and then eventually rocks, and eventually larger structures that are called planetesimals. Planetesimals are tiny, tiny planets, maybe the size of a basketball, maybe the size of a bus or a town, and then eventually as it coalesces, tracks together, you have the formation of a planet. These are the ideas that people have here. So the planetesimals are very small, that eventually would form into larger bodies of planets. We have at one time thought there were 9 planets, but Pluto is considered now to be a planetesimal, smaller than what we consider the cutoff for a planet, because we found more and more and more farther away from the sun, and we don't want to have hundreds and hundreds of planets. So we've defined a planet to be of a certain size. And so you have planetesimals forming planets, and then the gases forming the gas giant planets. So we have the first 4 being terrestrial, and the last 4 being gas giants. Anything that's left over is considered to be debris, and debris is either not had enough time to form into a planet, or maybe was a planet and broke apart by a catastrophe of some kind. But there is a debris field, 2 debris fields really in the solar system. You have the asteroid belt, which is between Mars and Jupiter, and then you have the Oort cloud, which is beyond Neptune. So there is various rocks and ice and all of these are circling the sun just like the planets are. Now, in the early history, when we were just looking at the solar system, looking at the stars, looking at the planets, and trying to map them, there was the original idea from Ptolemy. This was BC. Was the idea that you had a fixed stars. The stars were fixed at some certain point, kind of like on a ceiling, and then you had the Earth in the middle, and the sun and the moon and the planets would all go around the Earth. Later, there was lots and lots of evidence, especially in the Renaissance, of that this couldn't be. And one of the problems that they had was the fact that some planets, as it goes around, will actually stop in the sky and turn around and go the other way, and then stop again and go forward again, a retrograde type of motion. The best I can explain this would be if you were passing a car on the interstate and you're on the inside lane, you're going the same speed, you're on the inside lane, and so you have a shorter distance to travel, and so you are passing the car that's on the outside lane. And as you pass the car, if you were to look at this picture here, where you have a planet position, say, of Mars and the planet position of Earth, as you look at it, what's happening is you're seeming to change speeds. You're coming up on that car, which means it looks originally like it's coming towards you, and then when you catch up with it, it appears to stop, and then as you pass it, it appears to go backwards. So what's happening is this is evidence that Mars is not going around the Earth, but the Earth and Mars both are going around the sun. And that is what, during the early Renaissance, cost a lot of people a lot of problems when they were essentially arguing for this idea of the heliocentric model. So heliocentric is sun in the middle of the solar system with all the planets and comets, etc., going around the sun. Now, the first person to really do some work, mathematical work with this, was Johannes Kepler. And Johannes Kepler worked for one of the European kings. He was actually his astrologer, but while he was studying, he loved the stars and he was a math genius. He took a book that he found from his previous boss, who had his name was Tycho Brahe. Tycho Brahe had insomnia, and he stayed up every night, late, and he used his telescope to plot the positions of all the planets, just for something to do. And he kept a diary for 10 years. Well, Kepler found this diary and used the data in it to form 3 laws. I'd say one of the most brilliant things that man has ever done is these 3 laws of how does the planets actually work? How do the planets circle the sun? And the 3 laws, first of all, starts with the idea that the planet doesn't go around the sun in a circle. Instead, it's going around in an ellipse. And an ellipse, instead of having one point in the middle with an orbiting satellite, will have 2 focal points, with the sun being at one of the focal points. So you're going to have a time where the planet is closest to the sun, and then you're going to have a time when 6 months later or so when the planet is farthest from the sun. The Earth is closest to the sun in January and farthest from the sun in July. And so as it goes around the sun, that's the first of his laws, that it wasn't a circle that it's traveling, but it's traveling in an ellipse. Eccentricity is how much of an ellipse, how much of a cigar shape is that ellipse, how much closer to a circle, how much farther away from a circle. That's its eccentricity. So his second laws and his third laws are kind of related. His second law is saying that as it gets to the sun, it's going to travel faster. And as it gets away from the sun, it's going to travel slower. So there is a speed change of the satellite. And you're going to see this too when comets come close to the Earth or sun. It's going to speed up as it goes to the sun and then slow down as it goes away from the sun. A planet is going to have that too. So depending upon how circular or how elliptical the orbit is, will determine how fast it's moving and slow it's moving in its orbit. The inner planets are closer to circles. They're definitely ellipses, but the two focal points are really close to the center of a circle. As it gets farther away, you're going to get more definite ellipse shapes where you're going to have fast speeds and slow speeds. And then also he determined that the area of these triangles as it passes in the same amount of time are going to be equal to each other. So even though the base of the triangle at January is really, really big, the height of the triangle is very low. But in July, the base is very small, but the height is very big, and these are going to be equal to each other. And he was able to, just from that data, determine that these laws. Brilliant, absolutely brilliant. And then we're going to see gravity is what's pulling the planet around the sun, and gravity was first studied by Galileo and then later by Isaac Newton, and determining that you have an orbit of pull. There's a force that's pulling that planet towards the sun, that's keeping it from going in a straight line as it's traveling, instead making it go in a circular orbit.